years before time t1. Now, we're not changing the formula. We have this same process, but we're going to look at it from this other coordinate system, and what do we see? We see a process by which at 2, first thing that happens, see time is this way now, first thing that happens is a green thing and a black one come out, and later on the green one annihilates with the black one. To draw it turned a little bit, it'll look like this figure, which is a new process. This green line before used to go forwards, and now it's going backwards. So what we have to allow, and we have to include it in order to get any type of relativistic invariance at all, is a section of pairs running backwards. The possibility of a production of a pair and an annihilation by a disturbance. In other words, there must be antiparticles. In fact, because of this difference of the coordinate systems in two different speeds, so that which is ahead of which depends upon which way you look at it, we can say this, that one man's virtual particle is another man's virtual antiparticle. Therefore, first of all, antiparticles in pair production must exist, and second, antiparticles' behavior is completely determined by particle behavior. There's absolutely no freedom. You know what the particle does, you know what the antiparticle does. How? You just look at it from the other end. Because one follows one way and the other way. To summarize this very crudely, and I'll do this very much more accurately and fancy later, if we reversed everything, we would reverse the sign of x, y, z, and t, then we should be using an antiparticle. I call C conjugate, charge conjugate, or whatever it is, the difference between a particle and an antiparticle. And this change of the sign of time and the three directions of space. Let P represent what's called the parity operator, which changes the three directions of space. So PT is C, right? But we're finished. We understand why they're antiparticles, and we understand that wonderful theorem that CPT leaves everything unchanged. Okay? And therefore, since I've already done what I said I would explain, why they're antiparticles, I'm finished with the lecture. But in order for that's all there is to it. It has to be that they're antiparticles in order to get relativity. In order to determine the sizes of the amplitudes, this didn't talk very much about the sizes. There are lots of relationships among the sizes of the amplitudes, and this leads us in a new direction in which we're going to get a clue about the connection of spin and statistics, because the antiparticles are making new particles, and we'll see how it works. And the key to that is another proposition, and is that the total probability, I don't never can spell probability right because I haven't got the patience, of all the possible events, always has to add up to 100%. But let us analyze this in the lowest order. Suppose there's a potential disturbance A. We already talked about how a particle coming in at momentum 1 can be deflected to some momentum P with some amplitude A. The absolute square of that is the probability of deflecting a particle to momentum P. Actually, I include in A the wave function coming up if you look back at it. Now, we can also calculate the probability of not doing anything. That is, to leave the object, the original particle, where it was before. And this is, the amplitude is 1 plus alpha, where alpha was that diagram that we made before. And the absolute square is this thing plus that thing. It's complex conjugate, I mean, because 1 plus alpha absolute square is 1 plus alpha star plus higher order. And so there's a definite connection in size and sign that has to be right so that these two terms that added together will cancel this. In other words, that these two add up to a negative amount. I left out a lot of i's and things like that in here. We'll always put them back if you want them, but the point is these two things have to be this, that the probability of not doing anything is reduced from 1 by the same amount as the probability of doing something is increased. All right? So that the sum of doing something and doing nothing is still 1. So that connects this size and sign and everything to that. We can prove this way that B has to be A star but I don't need to bother you with that, so I won't bother you with that. Okay. Now, that was the non-relativistic case where we only had particles. Now we have a problem. We have added a new diagram, a new possibility. We not only have the 1 for the particle to go straight through, but the probability to do nothing is 1 plus twice the real part of this picture, which I'll call I, and twice the real part of this pair production picture, which I'll call Zwei. All right? Now it's easy to check, very simple, that twice the real part of this one cancels the probability to make a transition from 0 to p. That works. That's just the same as it did before. What have we done, however, is we've added another piece, and so we have to find out what it is that this absolute square is correcting for. All right? Well, if you work out see, the size of this and that are completely determined. As we just pointed out several times, that particle and antiparticle are absolutely related. So the size of this is completely determined. And this thing, you can work out, I'm talking about spin 0 particles now, it cancels the probability to make a pair with the electrons in O and the antiparticle has momentum p. That is to say, this is the negative of this probability. Now, what does that mean? You see, oh, that's easy. You say these are all the probabilities of producing pairs, but it isn't really, because you could produce pairs with any moment for the electron. And that's all canceled by something else, which is in a vacuum that we can come back to. But here is a special case in which we produce a pair with the electron in the same state as O. We have somehow, in order to make this all work, because this is a negative contribution, to say, in order to make it consistent, it has to come out that the probability of producing a pair with an electron in O is enhanced when the electron present in O. And that enhancement is what's being canceled. And that's the principle of Bose statistics that makes the lasers work. That if there's a particle in the given state, the probability of producing a new particle is increased. It's doubled, in fact. And this extra 1, 2 is 1 and 1. The extra 1 is the thing that's canceled by this, and that's how it balances. And so we can get a clue as to why the Bose statistics are the statistics for spin 0. All right? Now let me just outline it again. We've added an extra diagram, told us about a new process called pair production. We discover when we try to check the probabilities that this diagram makes a negative contribution. We have to cancel something, and that canceling is an extra probability for producing a positive antiparticle and an electron in the state O when there's a particle present originally in state O. And that phenomenon, that when there's a particle already present, the probability of producing another one is enhanced, is a characteristic of Bose statistics. And that's where it begins. That's to explain to you why it's possible. And if all you have to do is follow more details, more diagrams, more cases, and the whole thing will come pouring out. I've just given an example to show you which direction we're going to go. I'll just do one little example. If we didn't have any particle but started in a vacuum, then you can make a pair Q and P. And the probability to make, you see, you can make pair production, so that makes a particle Q and P. And the probability to make those pairs is sum over all Q and P of this absolute square. And that must be compared to the amplitude to do nothing. And the way that you balance that one is that you have another diagram in which you created a pair and then annihilated it. And if you take minus twice the real part of that, or rather, twice the real part of that is the negative of this. And so that's the way that balances. And the extra diagram we saw on the previous page is extra on top of that. So here's how all the pairs balance. And to finish it all off, what happens is that you find that you have to add all diagrams together. And you can see the exclusion principle with the positive sign. this way. Suppose you had 4 disturbing potentials and you produced 2 electrons with their positrons, and they annihilated again. And now suppose you compared that to what would happen if you produced these 2 pair, but instead of annihilating their own positron, they went across and annihilated the other guy's positron. That would make a figure like this. Well, this is a single loop, you see, and these are 2 loops, and you're supposed to add all the diagrams, so you add this and that, and it'll all fit together, and everybody knows that, and it's very simple, and it makes Bose statistics. Bose statistics, as a matter of fact, is not so very mysterious. As soon as we deal with anything like oscillators, such as the vibrations of a crystal which makes sound waves, we find that those sound waves obey Bose statistics, then we're adding all the amplitudes together. And so we don't find that quite as bad. What we're going to do is we're going to discover later that for each loop, when the spin is a half, each loop gets a minus sign. And therefore this has 2 minus signs for this 2 loops multiplied together, which is plus, and this is a single loop, which is minus. So when we change to 2 loops to 1 loop, we change from 2 minus signs multiplied to 1, and it's an opposite sign, and you get Fermi statistics. So I'm just focusing now. We have to look and understand why, with spin a half, we're going to understand later why there's a minus sign in the formula for the loops. Okay? Now I'm going to return now, because I have to be more careful, to go a little bit more into detail and to explain the relationship between the antiparticle behavior and the particle behavior. Of course, it's true, and it's still true, that the antiparticle is completely determined by the particle behavior. Let me analyze this a little bit more in detail in the case of spin 0. We noticed that for T2 greater than T1, that is above the plane here, the amplitude to go between 1 and 2 was this integral. I've chosen a special case of scalar couplings and so on because this form is relativistically invariant. The 2EP under the D3P makes a relativistic invariant volume element in momentum and energy. You have to check that someday. This E, energy times time minus momentum times position, is of course the typical relativistic combination of the product of the time components minus the product of the space components. And this is a relativistically invariant form, and I've chosen that one to study. Now, because that plane could have been taken anywhere, we know that all over the outside light cone, by just tilt the plane, if you want this point here, tilt the plane far enough down, take the coordinate system this way, and you'll get this function. It's always the same function because it's relativistically invariant. So this function is not only true above the plane t equals 0, it's true of the whole negative light outside the back light cone. That is, the space-like region and the future light cone. This formula is right. On the other hand, for t less than t1, and also space-like separated, since energy must be greater than 0 always, we have to have a form that the same amplitude is G21, I mean the amplitude in that region, either T2 less than T1 in the bottom light cone, or else inside with T2 less than T1 but in the space-like region, we'll have to have the opposite sign frequency with a whole lot of weights all added together in some complicated way. The question is, and in the region when T2 and T1 are space-like, we could use either one of these 2 formulas to obtain the amplitude. It's like a patching, and that makes the functions have to be equal there, and that's going to determine what this function has to be, this G, because we know it's equal F in that region. So the question is, if a T2 and T1 space-like, we have an expression with a negative frequency, can we express it also as a function of positive frequencies alone? Ordinarily, you can't do it. It's magic, but for this particular function, which is relativistically invariant, it's possible. Let me show you why. First, for T2 equal T1, F21 is real, because this isn't here. And when you integrate